In the late 1800s, physics treated time like a single, shared beat. A second was a second, everywhere, for everyone. If two clocks matched once, they stayed matched, no matter how they moved. Space and time felt like a rigid stage where events simply happened. This simple picture worked for engines, planets, and everyday motion. Then one thing refused to behave like everything else: light. Scientists assumed light traveled through an invisible medium, the ether, the way sound traveled through air. That idea carried a clear promise. If Earth moved through this ether, then the measured speed of light should shift slightly depending on direction, like feeling more wind when running forward. In 1887, Albert Michelson and Edward Morley tested that expectation with extreme care. The shift never appeared. Light acted as if no ether wind existed. That result was not a small glitch. It cut into the foundations. If Earth rushed through space, why did light's speed refuse to change? Physicists tried to patch the old story, suggesting that motion subtly distorted measuring rods or affected instruments in just the right way. But the fixes felt forced, and more experiments kept pointing the same way. Something basic was wrong, and the obvious suspect was the one thing everyone thought was untouchable: time itself. In 1905, a young physicist named Albert Einstein offered a clean way through the mess. He treated one stubborn result as non-negotiable. The speed of light stayed the same for every observer, even if they moved. That single move broke an old habit. People had assumed motion simply added and subtracted speeds. Light refused to cooperate. So Einstein changed what everyone thought time meant. If light always ran at the same speed, then something else had to give. It could not be space, because space did not set the pace for light. It could not be measurement error, because the pattern held no matter who measured. The only escape was unsettling. Two observers in motion relative to each other did not share one universal clock. Time had to adjust so light could stay constant. That shift reached deeper than clocks. It hit simultaneity itself. Events that looked perfectly synchronized for one observer did not have to line up for another who moved. There was no single God's eye now that everyone agreed on. Each observer carried a valid time that fit their motion, and the laws of physics still worked the same. The price was a new, flexible definition of time. Once the speed of light stayed fixed for everyone, an uncomfortable question followed. If light refused to add and subtract the way everyday speeds did, then something else had to give. It turned out to be time itself. Motion did not just change where things were. It changed how fast now moved along. A moving clock did not keep pace with a clock at rest. That claim sounded impossible until a simple clock made it unavoidable. The simplest clock imagined used light. A pulse bounced between two mirrors, and each round trip counted as one tick. For someone standing still with the device, the light travelled straight up and down, tick after tick, covering the same distance each time. But for someone watching the whole clock glide past, the light could not go straight. The mirrors moved sideways, so the pulse had to trace a longer diagonal path and still hit its target. Here was the trap. Light's speed stayed the same for both observers. The only way to cover a longer path at the same speed was to take more time. So the outside observer had to conclude that the moving clock's tick lasted longer. The clock ran slow, not because it malfunctioned, but because motion stretched the time between events. That was time dilation. Relative motion made time itself pass at different rates for different observers. The next step had to be simple. If motion really stretched time, the effect needed a clock that could not argue back. Nature already provided one. Some particles behaved like tiny timers because they changed into other particles after a fixed average lifetime. Start the clock, and a countdown began. If those particles moved fast enough, their own decay became a clear, measurable test of whether time stayed universal. One particle fit perfectly, the muon. It formed high in Earth's atmosphere when cosmic rays struck air molecules, creating showers of fast debris. Muons lived only about 2/millionths of a second on average, then they decayed. That sounded long, but it was not. Even at nearly the speed of light, a muon should have covered only a few hundred meters before disappearing, not kilometers down to the ground. Classical time gave a clean prediction. The muons formed far above. Their lifetimes stayed the same, no matter how fast they traveled, and most of them vanished long before reaching detectors on Earth. Only a tiny fraction should have survived the full trip through the air. That expectation set the trap. If ground instruments still recorded large numbers of muons, then something in the old idea of time had failed. Detectors on the ground kept counting muons, not a few lucky survivors, huge numbers. That result clashed head-on with the simple classical expectation. Muons had formed high in the atmosphere, and in their own rest frame they lasted only about 2.2 microseconds before decaying. Even at nearly the speed of light, that lifetime only carried them a few hundred meters. Yet they arrived after traveling kilometers. Physics faced a blunt choice. Either the muons somehow lived longer, or the measurements were wrong. The measurements held. Special relativity supplied the missing piece. For a moving particle, time passed more slowly compared with clocks on Earth. The lifetime that mattered to an observer on the ground was stretched by the gamma factor. At 0.998 times light speed, gamma sat near 16, turning 2.2 microseconds into roughly 35 microseconds. That one change flipped the whole prediction. With about 35 microseconds available in Earth's frame, a muon traveling near light speed covered close to 10 kilometers before decaying, right in the range needed to reach the ground from typical creation heights. The extra muons were not extra at all. They were the same particles, obeying the same decay law, while time itself ran differently for them in motion. The muons from the sky already acted like a natural test, but physics wanted control. So the test moved into particle accelerators. These machines pushed charged particles around and around with electric fields, driving them to extreme speeds. Muons could even be made on purpose, then injected into a storage ring. Now their starting point, their speed, and their path all stayed measurable. The question tightened. Did their inner clocks still slow down? At rest, a muon lasted only a tiny fraction of a second. Then it decayed into other particles. In an accelerator, detectors tracked that decay like a stopwatch, counting how many survived as time passed. Classical thinking offered no escape this time, because the distance travelled and the speed were known. Yet the fast muons lasted longer, not a little longer. Longer by exactly the factor special relativity demanded for that speed. And it did not stop with muons. Other unstable particles, made and boosted the same way, also showed lifetimes that stretched when their motion climbed closer to light speed. The pattern held across different machines and different energies. The faster the particle moved, the more its decay slowed relative to the lab. It matched the same simple rule, again and again. Time dilation stopped being a surprise and became a tool. By this point, the prediction sounded clear. Motion changed the rate a clock ticked, but proving it with human clocks had demanded a new kind of tool. Mechanical clocks drifted. Even the best quartz clocks wandered. Then atomic clocks changed the game. They did not rely on gears or springs. They used the steady rhythm of atoms, a natural beat that stayed the same, until relativity said even that beat would shift when the clock moved. An atomic clock kept time by counting a specific frequency from atoms like cesium as they switched between two energy states. That frequency acted like a perfect metronome, and it proved unbelievably stable, so stable that tiny effects stopped being invisible. Relativity did not need big speeds to leave a trace anymore. Even a fast aircraft, a mountain, or a laboratory setup could, in principle, push two clocks apart by mere billionths of a second. Those billionths mattered because the theory gave a number, not just an idea. A moving clock had to lose time by a predictable amount, and an atomic clock could measure the loss directly. When two clocks got synchronized, then took different paths and got compared again, the difference did not hide in the noise. It sat right there in the readout. Nanoseconds became evidence. Time dilation stopped being an abstract consequence and became something engineers could track. Atomic clocks had already shown they could spot tiny shifts in time. The next step was blunt and practical. Take one out of the lab and fly it. If relativity was right, a clock riding inside an airplane should not match a clock left on the ground, not by seconds, by mere billionths of a second. But that was enough. For the first time, time itself became something that could be carried, moved, and checked. In the early 1970s, a test in the spirit of Hafele and Keating did exactly that. Atomic clocks were synchronized, then loaded onto commercial flights and taken around the world, eastward and westward, while a reference set stayed behind. When the traveling clocks returned, scientists did not ask for opinions or impressions. They compared numbers. The result hinged on a clean prediction. Motion made a clock lose time, but changing altitude changed gravity's pull and pushed it the other way. The differences were small, but they were not random. The eastbound and westbound trips came back with different offsets, just as relativity demanded when Earth's rotation got added to the plane's speed. And the higher altitude flights gained time from weaker gravity, even as motion tried to make them fall behind. The final comparisons showed measurable shifts in the exact direction the equations said. Time had not stayed universal. It had split, and the clocks had caught it. The next proving ground sat far above the planes: satellites. Once clocks left Earth and rode in orbit, they stopped sharing the same conditions as clocks on the ground. GPS depended on timing so exact that a tiny error meant a big mistake in position. A receiver measured distance by reading how long a signal took to arrive. If the satellite clock drifted, the whole map shifted with it. Two different relativistic effects pushed those satellite clocks away from Earth time. First came motion. GPS satellites moved fast, and special relativity meant moving clocks ticked a little slower than clocks on the ground. But the story did not end there, because orbit also changed gravity. Higher up, Earth's pull weakened. General relativity predicted that in weaker gravity, clocks ticked faster. These two effects fought each other, but they did not cancel out. The gravity effect won, so the satellite clocks ran ahead overall. If engineers ignored that, the timing error grew every day and the calculated position wandered farther and farther from reality. Roads missed their turns. Runways shifted. The fix required building the corrections into the system from the start, so GPS stayed honest. By the end of this story, time dilation no longer sounded like a trick of math. It acted like a measurable, repeatable part of nature. The same effect that let fast muons survive longer also showed up in machines people built on purpose. Atomic clocks proved it with clean numbers. Aircraft tests backed it up. And once satellites entered the picture, the question stopped being whether time slowed down. The question became, what happened if engineers ignored it? GPS needed clocks to agree across thousands of miles, while satellites moved fast and sat higher in Earth's gravity. Those two facts pulled time in opposite directions, and both had to be counted. Without constant corrections, positioning drifted by kilometers in a single day. With corrections, phones, ships and airplanes got reliable locations hour after hour. So time dilation ended up in the most practical place possible, inside routine design. Satellite systems treated it like a standard setting, not a philosophical debate. Particle physics relied on it to predict what detectors recorded, and accelerators depended on it to match what unstable particles actually did. Compared with the old assumption that time ticked the same for everyone everywhere, this new reality simply ran the world.